Okay, I think we can go ahead and start the class. So don't forget your homework is due Thursday. I will upload the updated lecture notes on chapter 2 later tonight or tomorrow morning, just in case you may need them. But in today's lecture, we are essentially going to start talking about fluid dynamics. And we will specifically focus on Bernoulli's equation. But before talking about the Bernoulli's equation, we should back up a little bit and see what is going to or see the underlying reasoning behind this relationship. Underlying reason, essentially. Why does this equation hold true for the type of flow that we are going to focus on? And as it is the case for everything, essentially, in mechanical engineering, we are going to go back to the Newton's laws. Newton's law of motion. The Newton's law of motion in general are the basics of the classical mechanics, which we are a part of. Our whole mechanical engineering thing is a part of the classical mechanics in physics. So there are three main laws, as I think you have seen these laws before. The first one is called the inertia. Which essentially, inertia says for an inertial frame of reference, the fluid at rest or the thing object at rest tends to stay at rest, and the object in motion tends to stay at motion. The one thing that you need to make sure that you are clear about is that inertial frame of motion. What is this inertial frame of motion? This is something you will see, if you haven't seen already, in your dynamics as well. What is the inertial frame of reference? Did I say frame of motion? Inertial frame of reference. An inertial frame of reference. Frame of reference is essentially your coordinate system, your x, y, z. Your coordinate system can move by itself, which essentially means that the origin of your coordinate system is moving. Like, think about it this way: you can put your coordinate system on the surface of the Earth, right? And the surface of the Earth is essentially moving, right? An inertial frame of reference. This is a frame of reference. And an inertial frame of reference is a specific type of this frame of reference that can move or is moving, but doesn't have any acceleration. Acceleration is zero. So for an inertial frame of reference, first law of Newton's law tells us that the object that is at rest tends to stay at rest, and the object that is moving tends to keep moving at that same velocity without a change in velocity, essentially. Okay. What is the second Newton's law? Second Newton's law, again, for an inertial frame of reference, same thing. The summation of all the forces has to be equal to mass of your object multiplied by its acceleration. And force is a vector, acceleration is also a vector. So we're going to have essentially this one law is not one equation, it's three equations. It can have component of fx, fy, fc. And these are the things that we have seen many times before. So the third Newton's law states that when a body exerts force, let's say we have two bodies. When a body exerts force on another body, this other body is going to exert the same force, just in the opposite direction to the first body, right? Have we seen this before? These three equations? Yes. So we are familiar with the equations. And we are going to use these equations to derive or find one of the most famous equations in fluid dynamics that talks about how different particles in a fluid move. Okay. And again, the idea is to go from these laws, or essentially specifically the second law, this one, to go from this to the Bernoulli's equation, to find this Bernoulli's equation and see what it does and what it means, what it calculates essentially in a flow. But I assume you can understand from the second law that the Bernoulli equation is essentially a force balance in a specific type of flow. But what is that a specific type of flow? We are making some assumptions. What I mean by that a specific type of flow is that we are making some assumptions to simplify this equation and get to this Bernoulli's equation. Okay, but what are those assumptions that we are making? The first assumption we are making is that there is no viscosity. So what is going to happen to our flow when there is no viscosity? Essentially, the shear rate, which we saw in the first chapter, tau, if you recall, your tau was equals to mu du dy. You have seen this equation. You solved some homework problem, fairly hard homework problems with this equation that was based on this equation, the shear rate. So we are essentially assuming this shear rate does not exist with this first assumption. The types of flow in which the shear rate does not exist are called inviscid flows. Or the type of fluids in which the shear rate doesn't exist are called the inviscid fluids. And the type of flow which contain these type of fluids are called inviscid flows. That's INVSCID, in case you can't read my handwriting. Okay. But in reality, as you can say, there are no inviscid flows, because viscosity is a very important characteristic of fluids, of liquids and gases. But there are types of flow in which viscosity is going to be very non-dominant compared to other types of flow. So we can just neglect its presence, right, and its effects. Okay. What else? What are the other assumptions we are making here? The other assumption that we are making is that our flow, so the first one was we are dealing with an inviscid flow. in viscid fluid. The next assumption is that our fluid is incompressible. Incompressible fluid. So your density does not change. If you recall, we had this bulk modulus, but that was dP divided by d rho divided by rho, right? That density doesn't change, so your bulk modulus is going to be very high. Okay. So what are the forces that are present here? We don't have the shear rate, and incompressible flow is going to help us further in the calculations. What are the forces that are going to be present in the motion of a fluid? Let's say this fluid is moving, right? The first force that is present is a pressure force. And the second one is going to be your gravitational force. Gravitational. So essentially, what we have on the left-hand side is going to be pressure force, plus the gravitational force. Gravitational force is going to be equal to m multiplied by your mass multiplied by your acceleration. One thing that I want to make sure that you are clear is that there is a difference between the pressure force and pressure, right? Pressure is that pressure force divided by area. So to find the pressure force, we have to multiply our pressure by area, right? I just want to make sure that we are all on the same page. Okay. So for the next step, the next one, we have to look at the right-hand side of this equation, which is the acceleration and multiplied by mass. It is easy for us to identify the mass of the system, but the acceleration is going to be a little tricky. So to understand the acceleration of the fluid, we have to introduce some concepts first. Is there any questions so far? The first thing you need to make sure that you are clear on is the choice of coordinate system or frame of reference. Okay, we can actually have the Cartesian coordinate system, which is a more common one. X, Y, Z. So each particle of the fluid can be, the location of each particle can be X, I plus Yj plus Zk. So to find the location of each particle inside the fluid compared to the origin of your coordinate system, you have to essentially come with a vector that is X, Y, let's call this Z. X, Z, and my drawing is not very well. Let's say this is a point here. Right? You get the point though, hopefully. Or we can actually do the other side. That will look better. Y. Okay. But we have other types of coordinate system. The other one that we may use, and we have used actually in the previous chapters, is the cylindrical coordinate system, which we use r, theta, and z to find the location of each point compared to the coordinate system. What is r? R is the direct distance from your coordinate system here. That's the radius of a circle that particle makes around your coordinate system. Theta is going to be, let's say the particle is here. Theta is going to be this angle. So the angle it has moved from a specific frame of reference, and z is going to be the height compared to your origin. So the choice of coordinate system is important. But the thing that we want to take away from here is this position vector s. So position at each time, can be identified with a vector s. And we are going to use, we are not going to use any of the coordinate system specifically for today. So we are going to have a general, hopefully we will have a general understanding of the Bernoullis. But yeah. Any questions so far? No. Let's look at a two-dimensional motion first. X and Z. So this y-axis, we are not moving in this direction. The motion of a particle will look like this, right? The path every particle takes to move from a point A to point B, I don't know if we have talked about this before or not, but this path is called a streamline. Okay. And we can describe a motion of a particle inside a fluid by a velocity vector that is tangential to this path. Okay, so a streamline is a path a particle takes that the velocity vector is tangential to it, right? So at each point, your velocity vector will be tangential. We can describe the position with this velocity vector, which is ui, vj, and wk, right? In every direction. We don't really care about the y component here. And the speed of this particle is going to be the magnitude of velocity vector v and we are, for the Bernoulli's equation, we are essentially going to apply the second Newton's law on a streamline. So a path a particle takes to go from point A to point B, right? So inviscid flow, that was the first one, assumption. Inviscid, let me write it again. Incompressible. And along the same streamline. And to make it even simpler, we are going to assume the flow is steady. So at each point, there won't be any changes with time. What does it mean? It means that at this point B, at this point C, for example, if the magnitude of velocity is 3 meters per second at time 1 second, at time 10 seconds, the magnitude of velocity is still 3 meters per second. But this velocity can be different than the velocity at point A. The velocity at point A can be 1 meters per second. So the velocity can change along the streamline, but the velocity at each point won't change with time. Okay? So 4 main assumptions here to find the equation of motion. So we are looking for the equation of motion for a fluid that has these conditions. Okay, so sigma f equals to ma, and we are on a quest to find the acceleration of a particle that is moving inside a fluid from point A to point B with these assumptions. Do we have any acceleration here? Does acceleration has any term? Just think about it. So the changes of velocity with respect to time are going to be 0. Does this mean the acceleration is 0? No. Okay. What is the acceleration? To find the acceleration, let me magnify a part of this streamline here for you. Let's say this is point A moving, and this is your particle here on the streamline. To find the acceleration, we have to define 2 position vectors. Position vector S, position vector N. So this is your position vector along the streamline, right? And a position vector that is normal to the streamline. And we are not making any assumptions about the acceleration. So on this this is a coordinate system by itself, right? One of the axes is tangent to the streamline. One of the axes is normal to the streamline. So it is moving with your streamline, your coordinates. You are going to have an acceleration along the streamline plus a normal acceleration. Normal to the streamline. That's the most general case. Do we understand this? Yes? So we are essentially looking at this particle, putting our coordinate system on the particle that is moving. So the coordinate system is moving it by itself, right? And we are finding the projections of acceleration, the possible acceleration that we may have on each of these axes. Okay, so let's try to find them. What can we say about this normal acceleration? This tangential acceleration. We usually define acceleration as dv divided by dt, right? The idea here is that the velocity doesn't change over time at each point, right? But we have a fluid flow. So the velocity of a particle that was at point A at a certain time is going to be different because it has moved to point C, right? The velocity at point A has not changed. It's going to stay the same, but the velocity at point C has changed. And if your particle has moved from point A to point C, its velocity has changed. So a velocity of a particle that is moving on a streamline is actually changing with time, right? The velocity of that point. The velocity of that point has not changed with time, but the velocity of particle that is moving has changed. So how should we look further into this? How should we try to formulate this in a way that makes a little more sense? We have to play a little mathematics here. So let's multiply and divide this whole thing by ds. So we're going to have dv divided by ds multiplied by ds divided by dt. What is this part? This part is essentially your velocity vector. So we can say dv divided by dt is equals to v dv ds. Let's look at this acceleration again. So we have changed the formula for acceleration a little bit with a mathematical trick. This formula is telling us how much the velocity will change with your location. dv divided by ds, changes of velocity with respect to changes in your location, right? So essentially, based on the fact that your velocity, your particle velocity is going to change between A and C, we have come up with a term for acceleration, right? That's a specific type of acceleration, not the acceleration that is going to happen at each location. The acceleration that is going to happen for a particle as it moves from one location to another location. Does this make sense at all? Okay, so one acceleration. What about the acceleration in the normal direction? The acceleration in the normal direction, what can we say about an acceleration in the normal direction? The idea of the streamline was that it is tangent to the velocity vector, okay? And we are moving on the streamline. So there is no movement in the normal direction. That's by definition, right? The definition of a streamline tells us that there is no movement in the normal direction. Well, what does it say? What does it mean when it comes to the normal acceleration? Is this zero or not? Is the normal acceleration zero or not? We are not moving in the normal direction, right? But that's based on the definition of your streamline. We define a streamline as a line that is tangent to your velocity vector. But does this mean the acceleration in the normal direction is zero? We have one no. We have two no's, three no's. Okay. Do you have any other opinion? That's true. The acceleration is not going to be zero. Why is that? It may be zero, but in general term, it's not going to be equal to zero. Why is that? It is because you are going to have think about it this way. Your streamline is moving. Your velocity vector, the direction of your velocity vector is moving, which essentially means that if you go back to have you passed dynamics, or do you have dynamics this semester? This semester, but there are some people who have passed dynamics. Okay, so if you go back to your dynamics, and I assume you should have seen it in your statics as well. I don't know. You may have seen it in your statics. We had a thing called centrifugal force, right? And centrifugal acceleration. So when you are on a trajectory, when you're moving, and that the direction of your velocity vector is changing, which means that your direction of your particle is changing, you are essentially pulling the particle in one direction and then pulling it in another direction. There is some force that is being applied to it, right? And that force is called the centrifugal force, which is, in the most general term, it is also present here because we have the changes in the shape of the streamline, which we have the change in the directional velocity vector. Does this make sense? Okay, so this centrifugal force is always normal to your linear velocity direction. But how can we characterize this centrifugal force? Velocity in the normal direction, I'm sorry, acceleration in the normal direction is also defined as dv divided by dt. But here we are going to play another trick on it. We are going to, let's say we are looking at these 2 points, right? These 2 points. See, the direction is changing. So if I magnify this, this is the part of the streamline I'm looking at. They have a curvature, which means that they are part of a circle, right? The angle of that circle has moved, let's call it d phi. Okay, from point E to point F, right? How much the velocity has changed? The velocity, your velocity is essentially going to be your velocity at point E minus the velocity at point F. We know the velocity changes between 2 locations. Okay. But how can we find these changes in velocity? Do we have any? Let me actually do this. The changes in velocity is going to be equal to your velocity at point E or F multiplied by changes in angle. And there's actually simple calculations. You can find the projection of velocity vector here, but I'm not going to go into details for that. So let's just accept this. The changes in velocity between point E and F is going to be your velocity multiplied by changes in that angle. And this angle is related to this arc length, right? This is going to be your radius, right? Angle itself is related to this arc length. That arc length is your ds, right? The changes in your location from one point to another point, right? How much it has moved, that length, right? Which is going to be equal to your r multiplied by d phi. Do we remember this from dynamics? Or have you seen it in dynamics yet? Yes or no? You do remember it. So you do remember what was the centrifugal acceleration? No? That's fine. You don't need to remember. Pardon me? That's it. That's it. That's what I'm going to get at. Okay, so if you do the calculation, your centrifugal acceleration is going to be equals to v squared over r, which is r is going to be the radius of the circle of this circle, right? So this r is going to be changing. I don't want to go into the proof of this. This doesn't really make any sense for this course. But yeah, so let's just accept it. So we have 2 components of acceleration, v squared over r and v dv ds. So let's talk about these 2 accelerations a little bit, and let's see what happens if any of them are 0. If your acceleration let me actually write this down. So your acceleration is going to be v dv ds like s hat plus v squared over r n hat. Centrifugal acceleration and the changes in velocity with respect to your changes in position. Okay, what will happen if your centrifugal acceleration is 0? The idea was the centrifugal acceleration is responsible for the changes in velocity vector direction, right? So if that centrifugal acceleration is 0, your velocity vector won't change its direction. What does it mean? What does it mean for the streamlines? It won't. It will be just a straight line. Right? What if your centrifugal acceleration is positive? It's essentially going to force the direction of the flow to change towards the center of the circle you have here. Let me magnify this. So we have, the idea was we have the velocity vector here, velocity vector here. If your a of n is larger than 0, your velocity will gravitate towards the center, right? The direction is going to change toward the center. So in general, you will get this type of flow. Okay. I assume you understand what's going to happen to this if your a of n is smaller than 0. The streamlines are going to move in the other direction, right? Away from the center of your circle, the curvature circle, the curvature origin, whatever you want to call it. Okay. What if a of s is 0? This type of flow will be the case you're going to get if a of s and a of n are both 0. You're going to get something called the uniform flow. Okay. What if a of s is larger than 0? This is what you're going to see with the streamlines. They're going to get closer to each other. And if your a of s is smaller than 0, the streamlines are going to diffuse. So what does it mean? What does a of s larger than 0 mean? It essentially means as you go further, as you move along these streamlines, your velocity is going to increase, right? If it doesn't have anything to do with the direction, right? So you're not gonna get any curvature here. The streamlines are a straight line. So for all of these cases, a of n is 0, right? Because these are straight lines. They're just getting closer to each other because the velocity is increasing. And we're going to see what will happen to pressure in that case. Any questions so far? So we have the accelerations. We are ready to finalize the equation, the Bernoulli's equation that we were looking for. We have the, we know the pressure forces. We are going to see the pressure forces and the gravitational forces, and we are going to see what will be our essentially Bernoulli's equation. We are going to divide this into two parts, or one main part actually. Sigma f of s on, which is tangential in the direction of the flow, the streamline. So on the streamline, as you're sitting on the streamline and moving with it, what is the force you're going to see? And then we're going to have sigma f of n. But the idea was we are deriving this Bernoulli's equation along the streamline. So this will be the part that we will be mostly focused on. So sigma f in the S is going to be equal to m multiplied by a. Well, what is the acceleration that we are interested in here? That's a in the acceleration in the same direction. So a of s, right? So sigma f of s is going to be equals to m v dv divided by s. And since we are in a small derivative things, the m is also going to be delta m, which is going to be the mass of a very small, like a square-like particle that is moving inside the flow. We have the gravitational force here, delta W, and the pressure force here. And we want to find both of them. The gravitational force is essentially rho g multiplied by your volume. It's a very small element, so a small volume, delta volume. I just have to remember that rho g is equal to gamma. So gamma delta volume. What is the delta volume here? Or the volume that is of this small cube? That's all of its like length, width, and the depth multiplied by each other. Okay. But that is going to be, this W is going to have two components in the two directions, right? Let's say this is moving, and we are looking at sigma fs, right? W is in this direction. So we have one component in the s direction, one component in the normal direction, right? Or let me use another color. One component in the s direction, one component in the normal direction. We are writing the sigma f along the streamline, so in this direction. So what we are going to get is going to be delta W of S, which is going to be a component of this W, or delta W sine of theta. And theta is going to be the angle this makes with the normal axis. Okay, so we have the delta W. We have the gravitational force in that direction. What about the pressure force? Pressure force is going to be the pressure difference between these two locations, the top surface and the bottom surface, multiplied by your area. Well, how can we calculate that? The pressure difference between these two locations is going to be delta P, right? Just divide this delta P by a delta S and multiply it by delta S over 2, which is the, I don't want to go into that detail that much. So this is delta S between the two, and you start from here. So delta S over 2, delta S over 2. But eventually, if you do the analysis, what you're going to get is that your pressure force is going to be delta P multiplied by delta P divided by delta S multiplied by your delta volume. So the pressure force is going to be the changes in pressure between the top surface and the bottom surface, right? Multiplied by your volume. And the same is true for the gravitational force. We already have the gravitational force. Okay. Is there any questions so far? So you plug all of these in. Sigma of S is equals to delta WS, gravitational force, and then I'm going to get delta F of P, pressure force in the S direction. So plug whatever we have in, it's going to get negative delta W or negative gamma, negative gamma delta V sine of theta plus partial P or delta P delta S multiplied by delta V, which is going to be equal to M, which is rho multiplied by your volume, delta volume, right? So I'm going to replace M with rho delta volume, and the acceleration A of S, which was velocity dv ds. The other assumption we are going to make here is that we are moving in the direction of the horizon, which means that the sine, or let's not make the assumptions for now. So what are we going to have? These delta volumes will cancel out. And we are going to get this final equation. Negative gamma sine of theta plus delta P delta S equals to rho multiplied by your velocity dv ds. Okay. So what can we do about this term? If you go back to your mathematics, v dv ds is actually 1/2 dv squared by s. Derivative of v squared is equals to v dv, or 1/2 dv squared is equals, or think about it this way, if you want to take the derivative of x squared, if you don't know, this is going to be equals to 2x, right? But something that is hidden here is d of x, which is 1, right? So we are not just, the only thing we are doing here is that we are not assuming the derivative of velocity as 1. So let's replace that. We are going to get 1/2 rho dv squared ds. Let's multiply everything by ds. You're going to get negative gamma ds sine of theta plus delta P, changes in pressure, is going to be equal to 1/2 rho dV squared. Do we have any questions so far? No? Sine of theta, we can define the sine of theta. If you go back to a triangle, how do you define the sine of theta? It's going to be this divided by this, right? Okay. Let's go back to our streamline here. 0.1, 0.2, right? This is your ds. This is your theta, right? And this was our original, if you recall, that I had over there, x and z, right? And we had a y while we are doing a two-dimensional analysis here. So your sine of theta is going to be equal to dz divided by ds. Do we see that? Do we understand that? Okay, so if you replace that here, your ds sine of theta is going to be equal to negative gamma dz plus delta P equals to 1/2 rho dV squared. Again, we are moving along a streamline between two locations. So if you are doing that, these derivatives are going to be equal to the differences between the two locations. So we are moving on a streamline, point A and B, right? If you apply this equation between these 2 points, what you're going to get is to gamma z of B minus z of A, right? dz, essentially the difference in the height, plus P of B minus P of A is going to be equal to 1/2 rho V of B minus V of B squared minus V of A squared. And again, these are the assumptions we are making here. This is very important. Like the one assumption we made here was that this is incompressible. So when we were integrating here, we could just take the density out of the integral, right? I didn't go through all of the steps, but I am assuming you all understand this. So what does it mean? If you move things around, one thing, guys, I made a small mistake here. The derivative of these changes in pressure is always negative. So wherever you see that has to have a negative sign. I'm sorry about this. So what does it mean? Let's move things around a bit. Let's move all of the things with sign A, which like that pertain to location A to one side, and all of the things that pertain to location B to the other side. So you're going to get gamma z of B plus P of B. And what I did was move all of the things to the other side to make the positive sign, and then moving them back. Plus 1/2 rho V of B squared is going to be equal to gamma Z of A plus P of A 1/2 rho v of a squared. So what does it mean? It means that the addition of your gravitational force, the summation of your gravitational force and the pressure force plus your acceleration, that's actually you're going to be your kinetic energy, right? Is going to remain constant on a streamline. So gamma z plus pressure plus 1/2 rho v squared is going to remain constant. So you can apply this equation between any 2 points on a streamline, on a streamline. Okay? Do we have any questions? I guess I moved a little too fast because, or you guys didn't ask any questions. So that's all I have for today. We have to finish the class 15 minutes early. And we will finish chapter 3 on Thursday, and we will start solving problems. We will spend one session on solving problems on Tuesday, and then we'll start chapter 4. Chapter 4 is much more mathematical. We are mainly going to focus on, at least for the first part of it, we'll be focusing on the Reynolds transport theorem. Involves a lot of integrals, involves a lot of mathematics, so it may become a little confusing, or it may, it can get a lot boring. So just have to follow me. You have to ask any questions you may have. You are not the question asking crowd in general, right? But you can always ask questions if you had any. So that's it for today. I'm gonna stay here for a couple more minutes to answer any questions you may have about the homework. If not, see you on Thursday. Sure, yeah. Yes. Let me end the stream. Yeah, thank you.